Okay. This is the simple representation of the probability density function for a 1 values x1 or x2. But we have the mixture model or the general definition of the Gaussian model. Okay, Gaussian mixture model. Okay, so this is the probabilistic model representing of the mixture or the many mu or many sigma values or the variance values or the standard deviation values. Okay, so it's the probabilistic model to represent many mean or variance values, each of them called the components of Gaussian in the literature. Okay, but this is just simple, the mean and variance value. Okay, so but how can we visualize this thing? Assume that we have the data distribution like this one, n and x. Okay, and so we have the values like this one, and we have the values like this one. Okay, at each iteration we have this kind of values and this kind of values. So only one dimension data, x given in here like this one. Okay, and so how can we model this term if we have this notation in here? And so we can just write this function like the exponential function, but this could be a class 1 or class 2, right? So in the normal distribution we have only one mu, but one mu cannot represent these things, right? We cannot, because we must create the two mean values or expected values for this case, right? So in our cases we should give that. Firstly, we should define the probability density function in here like this one, but it is total values of the what? K1 and K. This is the class number K in this case, and so we need to give the sum rate of this term like this one, Pk. It's the prior knowledge or the weight of the K components, K mean value, K variance values, and we should define to what the normal distribution in here for what x given mu K and variance K, right? Yes, this is the combination of these terms. This is called the mixture model. Mixture, mix. Okay?
What is by K?
I will explain that. K is the component number, which means that in this case K is equal to the what? 2, right? Okay. And so Pk, which is equal to weight of K th components. For example, if we have the data in here 25 and we have data 75, okay, this is the x values. What's the values of Pk? We have total 100 values. Okay, and so for the first class P1 is equal to 25 divided by 100. Pi 2 is no. So this is not the empty space. This is the visualization. So, okay. 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 This is called to what? prior knowledge, prior probability, prior information, right? Okay. And so this is what PDF function, the normal distribution, just like in the previous case. Okay. And so if we have this condition, and then in this mixture model we have the two conditions like this one. We have pk is equal to what? 1. This should be between the 0 and 1 values. And also we should say that pk, k equal 1 to up to k class, must be equal to 1, right? And also n x mu k, variance k, is equal to the what? 1 divided by square root sigma square k exponential minus x mu k square divided by 2 times square k, right? This is the normal distribution for the k. So how can we find the best mu pk, mu k, and sigma square k value? How can we do that? Because in the first place we don't have any knowledge about the 25 or 75, but if we have this data, maybe we can change, or we can find the probability values or these values by using the what? Some maximization method, which we call it to what? Expectation maximization algorithm. What's the meaning of expectation maximization algorithm? Yes. Yes. And in each case we have the 3 values: pi, mu, and sigma, right? And so we need to maximize these values, or we need to maximize the probability values for a given pi k, mu k, and sigma k, right? This is simple, but how can we do that? In order to implement this algorithm, expectation maximization rule can be used. We call it the EM algorithm. This highly utilized algorithm to what? To find the best parameters for a given what? The distributions. Okay? And so the main objective is that find pk, mu k, and sigma k values. And so in order to do that, we need to build the joint probability model. What's the meaning of the joint probability? Joint probability means that it is the summation of the whole probability in the what? In the log domain, because we have the exponential function in here like this one, and so we can say that this is the R cost function, like in MLP application or the logistic regression, but in terms of the probability distribution in this case. For example, if we have the n data in here like this one, greater n is the number of the samples, for example 100 or 200, and so we need to take the logarithmic values of these terms, and then k1 k must be implemented with what? pk and normal distribution xi mu k and variance k. Okay. In each case we have to what? Each xi value is evaluated for each class, and in this domain we take the log domain in here like this one. For example, the log domain is the entropy function, Kalbeck Liebler entropy, or it is the what? It is the area form of this function, because if you take the logarithmic values of the exponential function and then we get the area of this exponential, right? Just for example, if we have the ln function in here like this one, and so if we take the log or ln values in here, and so we take the whole area as a scalar values in here. Taking the logarithm of these terms gives us to what? Area. For example, 1 and 2. In each area, exponential function, this area is equal to the 1. The total collection of this area is equal to the 2 in the logarithmic space. Okay. So, this is the basic representation of what each data should be given in here, and log should be taken in here like this one, k equal 1, k, and pk, and xi given mu k and sigma k square. Okay. So, how can we minimize or maximize this algorithm? This L should be maximized for a given what? Pk, mu k, and sigma k. Okay? This is the what? The neural network coefficients or the model coefficients. But we want to maximize this area, because if we maximize this area, and then this is the best model to represent our algorithms, right? So, firstly, we need to initialize all the coefficients in a random way, like this one. GMM parameters, for example, pk, mu k, and sigma k square. Okay. After that, we should assign the new variable in here. Assign vik, responsibilities. This is the generic form, but these responsibilities means that vik is equal to the what? Pk times n xi mu k sigma k square and total class. Okay? J n xi mu k and sigma k. This is the what? This is the total probability, and this is the each class probability. And so this responsibility depicts or demonstrates of the what, how affect the pk or the other parameters to the total probability. Okay? This is called the responsibility. Okay? And so in each maximization step, we use these terms in here and update the what? Mu k and sigma square k and pk. Okay? And we check to what? L maximize. Okay? Until to the what? Until to the, for example, if we want to check this term, for example, 1e minus 4 is the maximization rate at this case, for example. Okay? This is no. This is the condition. For example, if we have the L max and L must be smaller than these terms. Okay? This L max is assigned in this data set because we have the what? The 1 values at each case, but that's not possible. But if we have this notation in here for a given class, and then we should converge to what? The maximum values of these terms. Okay? Yes, but we will implement right now. Okay? Okay? And so in the 2D GMM implementation, we should give this later or in the next week, I think, because it's not enough it's enough for this week. And so now we need to implement to the what to our algorithms on the Python applications.
In general, gradient descent gives us a local lemma. So here we have to convert the y-axis to L max minus L to get the lemma, not L.
Yes, but it's kind of a gradient descent based algorithm, but it's based on the Newton-Raphson method at all the time. But it's not can be called to the what the gradient descent algorithm. But it's just like that, okay? Because we want to maximize the whole algorithms in here. Okay, so we need to write this code or this implementation at each case in here. Okay, so firstly we need to open the VS Code in here like this one. And then firstly week 10 1 PDF function body in here like this one. Okay, so import numpy as mp and import matplotlib pyplot as plt. Okay, firstly we need to seed value set to what the 42 for example. Original data can be created with what the mp random dot normal function. Okay, in this function location means that the mean values, for example 5, scale value is equal to the standard deviation. Okay, and size value is 1000, which means that we have the 1000 random data in here. Firstly we need to give the what mean original values in here like this one. mp mean creates to the what the original data. Okay, and also we can calculate to the what variance like this one var. Okay, and then we can print the whole this value mu and mean original aynen mean original and var variance original. Okay, these are the model parameters. Okay, so how can we convert these terms or derive the manual normal PDF function in here? We should give the x, mean and variance values. Okay, and after that return values 1 divided by mp sqrt 2 mp pi times variance, right, and mp exp minus x minus mean square divided by 2 times variance. Okay, these are manual normal PDF function, right? So for this model we need to give the generate new data set in here like this one. Test data is a random data. mp lin space is given in the what the mean original data and max original data and 1000s. Okay, this original data is different from the test data. Okay, this newly one. And so PDF values manual is equal to the manual normal PDF function with test data and mean original and variance original, right? This test data is not the original data, but if we take this mean original and variance original for a given the test data, and then we can create the probability distribution for new data, right? And so visualize PLT figures like this one, fig size 10:6, and we need to give the histogram values of this data. PLT hist, the original data means 30 and density is true, and alpha 0.5, color is blue, and label is equal to the original data. Okay, histogram class means that we split every data into the 30 parts. Okay, 30 parts, 1 bins or 1 bar. Okay, plot test data, PDF values normal and color green, and label manual PDF. Okay, so PLT X label should be assigned with the values, and PLT Y label should be assigned with the probability density. Okay, and PLT title probability model. Okay, and PLT legend is code, and PLT show must be code. Okay, and so if I run this code, and then we will have this model. Firstly, you need to see that the test data is given in here, but in this original data is a histogram values, right? This is the histogram of this data. But if we take the new test data, not the original data, we have same kind of probability rate at this time. Okay, this is our model, and we can model everything about that. Okay, this is the basic implementation of the probability density function. Yes, we assume that. We don't have any chance to model the otherwise. Okay? Here. We need to assume that this is the normal distribution, or this distributed in a normal way. Okay? Okay. So, in the second example, we need to move with the PDF classification. Okay, in the PDF classification, we set 2 class with the mean and standard deviation values or the variance values, and then assign each data to the 1 class. But this PDF function must give to the to this representation in in a way of the probabilistic way. Okay, so in this time should give the MP random seed should also be given in here. Class 1 data should be assigned with the MP normal random, normal, location is 5, scale standard deviation 2, and size 100. Okay, this is the class 1. Class 2 data is the MP random, normal, and the location 10, scale 3, and size is equal to the 100. Okay, and each case we should give the what the mean class 1 is equal to the what the MP mean. What's the meaning? Class 1 data. In the second case we should give the what? Class 2 data. Yes. And also we should give the what? Variance. Variance class 1, variance class 2, var and var. These are the what are model. Okay, so manual PDF is the same in this case, and so I can copy of all of these things in here like this one as a function. Okay, so how can we generate test data? Just notice that the test data is different from the original data, but we may have obtained the probabilistic way of these terms. Okay, and so we can check the model is true or not, right? And so test data can be created with what the MP linspace, with the what, with the values of the what the mean, and mean to the what, I'm sorry, mean class 1 data. Okay, and mean class 2 data. Okay, because we have 2 class. Yes, we should find the minimum values of the what? 2 class data. Okay, and so we also give the max to the what? Class 1 data, and max class 2 data, right? And after that we should give 1000 data. Okay, we check and that's okay. Okay, and so after that we should give the PFD values class 1 manual normal PDF with the data of the what test data, and mean class 1 and variance class 1. Okay, and after that we should give the 2 because we have the 2 class in here, right? Yes, we have 2 distributions like in the what, like in the PowerPoint presentation. Okay, and so how can we classify this condition? Classification results can be assigned to the what the MP, where this returns to 1 and 0 values. This is just simple equation. PDF values class 1 if is greater than PDF value class 2, and we can say that which is class 1, otherwise class 2. Okay, this is a simple idiom to use the where function. Yes. So PLT figure fig size is equal to the 10 and 6 or 12 6. Okay, and so PLT scatter must be used in this case because we have the 2-dimensional data, class 1 data, MP zeros like class 1 data, and color blue, right? It's the blue, and label equals to class 1 data. Okay, and also we give the class 2 data, but in this case we should assign zeros. Okay, because we have the label in here like this one, but we need to change the orange. Okay, in this case we have the orange values and blue values, and we set that the scatters is assigned to the different range, and we can see all the class. Okay, this is like function. This is obtains the length of this class 1 data and assigns to 0. Okay, just like that. But for in the representation you can see that in running you can easily see that. Okay, PLT plot should be assigned test data and PDF values class 1, and this is the color green and label class 1 PDF. Okay, and also class value 2, and also this is red and label class 2 PDF. Okay, so highlight classification results on this plot. PLT scatter should be given in here like this one. Test data is classification results is equal to the class 1, right? This returns to the this condition is true, and test data returns these values in here. And MP zeros like to this one. Okay, and S is equal to 50, and label this is equal to classified. S, huh?
What is this?
S is means that this the size of points. Okay, classified as class 1. Okay, and also we should give the blue marker in here, because we need to give this marker like this one. It's the S, and color equals to blue, and also marker is equal to X. Okay, just like this one, class 2 and class 2, but in this case marker is maybe X because the color is different, orange. Okay, we can say that the marker is the same because we have the different range. Okay, so PLT X label values and PLT Y label does not enough in here. Classification probability. Okay, and so PLT legend and PLT show. Okay, and so if I run this code, and then we have this kind of information. Okay, so class 1 data in the test data assigns these terms like this one, and class 2 data is represented by this one. Okay, and this is what? Yes, it's the split, it's the intersection point of this term, and so this area may be class 1 or class 2. We don't know that, but in this representation like this one, classified as class 1 is in terms of in this one, and so at the right hand side of the class 2 we have no problem because we have the 0 probability in this case. But In this case, at the left hand side of these terms, the probability 1 is greater than probability 2, and we can assign that to what? Probability 1. What? For example, at the 7.5, we may have the probability 1 and probability 2. Yani class 1 and class 2 can be contained in this domain, but we don't know that. This is the... Yes. Yes. Class 2, because we have the highest probability in there. Okay?
So we can say that the intersection point is just three short places.
Yes, because we have...
On the right we have a plus, and left it is a different plus.
Yes, because the MP where is given in here like this one, for example. Okay? Because the PDF class 1, class 2. But if I have these terms like this one, 0.7. Yes, we scale this algorithm, and then the 75 is the class 1, right? Or if we take the 0.2 and just like that, look, or 0.1, right? Just see the green line. Green line is that class 1, right? And class 1 is increased at this case, because at each small probability we have the correct situation, or we assign the correct values.
The concept is the same of the focal loss for balanced data.
Yes, we can.
Concept is the same.
Yes, concept is the same, but we can assign this parameter to scale our PDF function to set the different regions or different probabilities. Okay? At 5 plus PDF 1. And so in the third case, we need to build the what? GMM log likelihood function. It's the last code we will implement, but it's directly related to what? The expectation maximization algorithms. Okay? Okay? So, week 10, 3, EM for PDF.py. Okay? So, I can easily set that import numpy as mp, import matplotlib.pyplot as plt. Okay, mp random seed 42 example. Okay, and data class 1 is equal to the mp random normal function with the location of the what 5, scale 2, size is equal to 250, and data class 2 is assigned to what 24 and 1.2 and 75. In the first place, we should say that the data class 2 prior probability, which is equal to the what 75%, because we have the 75% data.
Our B here is like 75%.
Yes, but the algorithm, expectation maximization algorithm, can detect it by using these terms. Okay, automatically. Because it's the R data 1 class and data 2, but in a real-time application, on real case, you don't have this information. I can generate this data, okay? And so in the normal case, we don't know the mean and standard deviation values. Yes, but in the real-life application, you have data class 1 and data class 2. In the expectation maximization algorithm, we try to find the mean and these values. Yes. Okay. And so the original data is the what? The MP concatenate is the what? Data class 1, data class 2. Okay, and PLT plot is the original data, color blue. Okay, PLT title, original data, PLT X label, sample numbers, number of samples, PLT Y label, data, and PLT show. Okay, like this case, I have drawn this picture in the what? In the expectation maximization algorithm or the Gaussian mixture model. Okay, this is our signal. Okay, so how can we find the mu or sigma values or the pi responsibilities or the prior knowledge values in here? Firstly, we need to define the Gaussian PDF again in here, like this one, x, mean, and variance value, and we should take these values like this one. Okay, just a simple formation, and we should give the what? The def GMM distribution, like this one distribution. We have x, pi, means, and variance values in here, and we should return to the what? The summation, because sigma k equal 1 to k or times pk times normal distribution, right? And so pi k times Gaussian PDF for the what? The x and means k and variance k, right? For the what? For k in range of, for example, ln pi. For example, so we can say the mean or variance value, but the pi is, if we have two classes, 2 pi is given in here. Okay, this is the summation of the what? The total probabilities. Okay, and then we should give or define to the what? The log likelihood function in here. Def GMM log likelihood, which means that this creates the joint probability, the summation of the whole probability in an area form, right? And log likelihood can be given with data, pi, means, and variance values, right? And we should return to the what? The sum MP log LM value in here, GMM distribution with the parameters of what? Data, pi, means, and variance, right? This is simple. This whole needs what I want in here, right? Okay. So, how can we build the expectation maximization algorithms? In order to do that, we need to give the data number of components. In this case, we have the what? 2 components, right? And after that, max iterations should be given in here. For example, 100 default values and tolerance. For example, 1e minus 4. Okay, this is the default value. We can change these values in real-time application or in training paths. Okay, and so yes, this is the hyperparameters. Firstly, initialization must be given in here. Pi must be assigned with what? MP once, num components divided by num components, which means that we have 2 values in here, but the num components 2. And so if we have 2 class, each pi assigned to the what? 0.5. 50%. Okay? Yes, this is the initial values. And it's the highly efficient values. Okay? Maybe you can assign the 1 pi is equal to what? The 0.1 and the other 0.9. For example, you may choose that. But this is the efficient way to assign the initial values in here. Formal representation. We assume that each class has equal representation distributions. Yes, these values is change at the training phase. Okay, means can be assigned with what? Anti-lin space, min data, max data, and num components. Because if we have the two components and we have the two mean values, right? Okay. So variance can be assigned MP once with the what? Num components. 1 and 1. Okay? You can assign the different values, but I choose that. So, what's the expectation state in here? If we assign to what? 4 in range of what? What? Yes, max iterations. What's the meaning of this? Yes, this is the pseudo number, the underscore term, which means that we don't have the any in this for this operation. For example, if I choose the for I, and I can use the I, but I cannot use these terms. Okay? Or the in this is not important in this case. Okay? And so, we should calculate firstly to the what? E step, expectation step, responsibilities, right? Responsibilities. Okay? And so, MP array can be given with the what? It is definition pi k times Gaussian PDF with terms of data and means k, right? And variance k, right? Variance k and 4 k in num components. Okay? This is the responsibilities. In each case, we should give this notation, and after that, this is the k components, and we should give the what? Responsibilities divided by equal to the what? Responsibilities sum, but x is 0, right? Total responsibilities. Yes, this is the expectation step. And so, how can we create the maximization step? Firstly, pi is equal to the what? The responsibilities mean values. At what? Axis 1. Yes? No, so this responsibilities is the what? Is the no. For a given class, we have the normal distribution and the pi values, but in this class, the responsibility means that which data is responsible for each class. And so we have the total probability in here like this one, but the class 1 responsibility is, for example, 0.2, the other 0.8, for example. Okay? And so we see that, or we understand that 0.2 is the responsible for class 1, and we need to update that pi by using these responsibilities. because we have the 0.2 effect on these pi values in this case. Okay? Means should be assigned with what? Responsibilities times data, sum x is equal to 1, and responsibilities sum x is 1. What's this derivation? This derivation directly coming from what? Log L function is derived, or the derivative terms with respect to the pi gives us this formulation. This is the update rule, like the gradient descent algorithms. Okay? We define the L function, the total summation of the log blah blah blah, and if we take a derivative with respect to pi, this notation is obtained in the update rule. If we take a derivative with respect to the mean values, and then we have this formula. Okay? And the variance can be updated with the what? Responsibilities times data, means MP new axis times square x minus mu square. Okay? And we should give the what? Sum x is equal 1. Okay? And this must be divided by to the what? Responsibilities sum x is 1. Okay? It's not easy formulation, but this is the true formulation. Okay? If you take a derivative of the maximization function with respect to pi, means, and variance value, you obtain this formulation. Okay? After that, we should compute the likelihood, like this one, log likelihood is equal to what? GMM, log likelihood data pi means and variances. Okay, because we need to observe the what? The total cost function in here. Log likelihood is a cost function, and new values should be passed this function, and then this function should be checked with what? If this term is greater than 0, because in the first update we should initialize the data, and so we need to pass the first step in here, and MP absolute value of the log likelihood minus previous log likelihood is smaller than tolerance and break. Okay? But prev log likelihood should be updated with what? Log likelihood. This is why we need to pass the first step. And so this tolerance is small, which means that we maximize the rate of these terms. Okay? Okay? So at the end of this code, we should return to the what? Pi, means, and variance values. Okay? So run EM algorithm in this case. Firstly, we need to give the num components like this one 2, okay? And we should give the pi, means, and variance values, which is equal to the what? The expectation maximization algorithm. We should give the original data, num components, okay? And max iteration 1000, and tolerance is 1 minus 7. Okay? if I run this code and then expectation maximization algorithm returns to what the best pi, means and variance values. Okay, after that we should give the what the f pi is equal to the what pi, and means is equal to the what the means, and variance is equal to the variance. Okay, these are the correction values of these terms, and we also give the STD, standard deviation values, with the what and P SQRT variance. Okay, so if I run this code, pi 0.5 7/5, right? Means 5 12, variance 3 7 1 3, and STD 1 9 1 1. And so in the first place the location 4.99, location 24 and 24 is closest. Okay, and scale is 2, right? 1.9 standard deviation, and scale is 1.2 1.18, it's the closest values, and 25 data 21, size 75 data 75. Okay, and so if I change this code like this one, and so if I rerun and then just look at that, right? No, it's not good or enough. This is not the true or false game system, but we have this distribution like this one, and so we can find the pi value and means value and variance value by using these terms. Okay, for a given any class.
In general, embalanced data sets is not good to work. In general, embalanced data sets is not good to work.
Yes.
You have to use something like focus or something.
Yes. In this case, we have ideal data. Okay, and so we have the normal distribution based on this data. But in the real life application, you can close the data for your model. Okay. Okay. And so how can we visualize these terms? The GMM, probabilistic rate. We need to give the PLT hist values like this one, the original data, means 30, and density true, and alpha 0.5, opacity, color is blue, and label is original data. Okay, and X range can be defined in here, MP lin space like this one, mean original data, max original data, and 1000. Okay, and GMM distribution values can be defined in terms of the MP array like this one. GMM distribution X pi means and variance, right? But for X in range, no, X range, because we have the MP lin space. Okay, max and mean data, right? And so PLT plot also given for the what X range, GMM distribution values, color red, and label GMM distribution. Okay, and PLT title GMM for 1D data. Okay, PLT X label values, plt y label probability density, okay, plt legend, plt show. Okay. Hı?
BLT.legend vermesek de oluyor. Neden kullanılıyor?
Label GMG dist right here and original data in here. Okay. The blue line is the original data and this is the line. Okay. But you may choose the blue line in here and we can see that this one, but the GMM distribution models this data. See, it's correct. Or 1000s in here like this one. Or what happens if I choose the 7? What happened? Yes. Yes, it's too close to each other, right? But if I choose 9 in here, yes, but we have the small line here, right? For example, if I choose different color in here, the 75 at this stage, and so we have 1D distribution, but with the correct values of these terms, like the variance and the other terms is normal distribution. Okay, and so if we have this kind of information, we can generate the many components like this one. We can generate by using the expectation maximization algorithm. 8 components can be defined in here, but in the next lesson we will talk about it, not this lesson, because I'm tired.